So let me make you quickly revise the inductor. As I have already taught you somewhat of the inductor, I will make you quickly revise the formula. So we have seen that whenever there's a like coil or a, I can say, solenoid, and there's a changing flux in that. What, because of its own current, because of its own current. If the current is there and that is changing, what will happen? According to this formula n phi equal to Li, we are going to get the self inductance. Okay. So and that coil or the solenoid is only known as inductor. So usual notation of inductor is like this. Then I told you that EMF in this is going to come minus L di by dt. And when you apply the Kirchhoff's law, how will you are going to apply the Kirchhoff's law? If current is like this, so in this direction we are going to write minus minus L di by dt. So voltage drop in the direction of current, and while in opposite direction we are going to write plus L di by dt. I hope you remember this. Okay. So whenever you are going to apply Kirchhoff's law, we are going to use this way: in the direction current minus L di by dt, and in opposite direction plus L di by dt. That is going to be the voltage drop or gain, whatever you say. So now what has happened? What happens? Like as I told you, what is the work of an inductor? The main work of an inductor is whenever there is a changing magnetic like electric current, it is trying to oppose the change. Means if the current is decreasing, it will try to increase it, and whenever it is increasing, it will try to decrease it. So I already made you derive the formula of potential energy, half Li square, and I said you that this energy is going to store as the in the form of magnetic field, or in the magnetic field this energy is going to store, where energy density comes out to be half b square by mu naught. Okay. So after going through this, I told you that whenever there is a change in inductance, okay, what is going to happen? This formula is going to help you. L1 I1 is equal to L2 I2. For example, by the way, what is the unit of inductance? Henry, I have already taught you. So for example, suppose if I said a question, uh, in a circuit, the current through an inductor of 2 Henry is 1 ampere. If inductance is changed, okay, by inserting a core, iron core, to 3 Henry, find current just after core is inserted. So whenever we are going to insert a iron core in an inductor, you know the magnetic field inside will become more. Okay, you remember the magnetic properties of material. There we have seen, if you take any material in that, magnetic field is going to increase. So in this question, what will happen? The inductance is going to increase to 300. So we can apply the formula L1 I1 is equal to L2 I2. Okay. So what is L1? 2 into what is ampere current? 1, which is L2. Sorry, this is L2, which is 3 into I2. So just after the insertion, I2 will become 2 by 3 ampere. I hope you understood this formula. Okay. Now I said that series and parallel grouping of inductor. Series. So first of all, series grouping. So suppose this is L1, this is L2, and so on. Okay, this is Ln, and they are suppose in series. Voltage is V. So what we are going to write? Current is going to be same in all of them. So here voltage drop V1, voltage drop V2, here voltage drop Vn. So what we'll write? V equal to V1 plus V2 plus up to Vn. And instead of all of this, if you take a single inductor of L equivalent, which will draw same current I. So we can write V equal to minus L di by L equivalent di by dt. L equivalent di by dt. For this equivalent inductor, you can say. So that is equal to V1 for first inductor minus LD I by dt. Current is same in all of them. So minus, so this is L1. Similarly L2 di2 by dt, and so on. So you can see this di by dt will cancel out and we'll get L equivalent is equal to L1 plus L2 plus so on. Same like a resistor. Now we are going to do the parallel one, parallel combination. Parallel combination. So what happens in parallel combination? Suppose this is the parallel grouping of inductors. Okay. So in parallel voltage, this is L1. Voltage is going to be same in all of them, but current is going to be different. I1, I2, here IN, okay, here I. And equivalently, we can take a single inductor L equivalent and voltage V and current same I. So we can write I equal to I1 plus I2 plus so on. So what is I? So we know V is equal to minus L D L equivalent di by dt for the right side. Similarly, for right left side, we can write V equal to voltage is same in all of them. L minus L di1 by dt minus L2 di2 by dt and so on. Okay, so on. So finally, we can write L1 di1 by dt is equal to minus L di2 by dt so on, and that is also equal to L equivalent minus L equivalent di by dt. Okay, now dt will get cancelled and we can write L equivalent di is equal to minus L1 di1 is equal to minus L2 di2 and so on. So we can write L equivalent into I minus is equal to minus L1 I1 minus L2 I2 is equal to, this is equal to, sorry, so on, equal. And also we know I equal to I1 plus I2 plus so on, right? So let's this whole thing call it K. Then what you can write I? I can write a K by L equivalent. And by the way, this minus minus will get cancelled on all of them. Similarly, what you can write I1 as K by L1 is plus I2 as K by L2 plus so on. And K will get cancelled and we are going to get L equivalent is equal to 1 by L equivalent equal to 1 by L1 plus 1 by L2 plus so on. I hope this is clear. Okay. Now, next is our mutual inductance. And before going to mutual inductance, the question which I gave in class, this one, two parallel plates are there. I asked the to find the uh, like self inductance. So for unit length. So I have sent to you that question in group, the solution of that. This was D, and I have taken unit length. This is also one. This is also one. So what is the flux? We have seen in class that mu naught J by 2 into is the field, and this is the considered area. So flux will come B into this area, which is 1 into D. This was the thickness D. Okay. So this will behave as a single turn only. So N is equal to 1 only. So by the way, flux is equal to Li. Okay. So what is I? J into width 1 and flux is B into D. So from here L will come how much? By the way, what is the magnetic field B? B is, we can write the value no? Mu naught J. Mu naught J here. So simply we are going to get L is equal to JJ is going to cancel and mu naught by 2. Okay. Now come to the mutual inductance. So as I have told you in class, whenever there are two coils and because of one coil there's a flux change in the second coil. we what will happen is second coil some induced EMF will be there. Okay, because of one, like your friend is influencing you na. So see, in just a simple example, like one influence comes by yourself, that is self inductance, and one influence comes by your friend, that is mutual inductance. Just for fun, like I'm telling, but similar thing is happening here, that when the sideway current or sideway loop is producing some magnetic flux, like a field, okay, and hence flux, and if that is changing, because of that there will be some induced EMF in the loop, that is called mutual inductance. So already I have made you write formulas, m phi equal and reciprocity theorem and everything. So let's try to find. So already I made you write the formula, so go and check through the class notes. So now let's check the mutual inductance for two concentric solenoids. So suppose for example there are two solenoids. Okay, one bigger one is smaller one. So bigger one is having n1 number of turns, smaller one having n2 number of turns. See, remember as per reciprocity theorem, mutual inductance, either you find because of bigger one into inner smaller one or a smaller one into bigger one. Both are going to come the same. Okay. So here, what I am going to do, I am going to find the mutual inductance because of the bigger one into the smaller for the smaller one. So suppose I am assuming the current in the bigger one is I1. So what is the magnetic field? So and let's assume the radius is B for bigger one R1 and for the smaller one R2. So what is the magnetic field inside the big that bigger one solenoid? We know magnetic field will come if this length is L. So B will come mu naught capital N1 by L into I1. That is the magnetic field because of bigger solenoid. But the thing is, if you see from cross section view, so this is the bigger solenoid which is of radius R1 and the smaller is of R2. So in a smaller one, the flux will miss like area is up to this small this area is this small part only, na? The small part only. So in that what is the flux? Flux will come phi and also number of turns n2. What will come? N2 into phi, which is b into pi r2 square. Only that much part. So n2 into what is b? Mu naught n1 I1 by L into pi r2 square. So that is equal to n2 phi or total flux. Now according to our definition, what we have know that n2 phi is equal to m mutual inductance, n2 or phi 2 due to 1 flux into due to 1 is equal to mutual inductance into I1. So if you keep these values, so N2 into mu naught, here I will write it together, N1 N2 I1 pi R2 square by L is equal to M I1. I1 is going to cancel and we are going to get mutual inductance as mu naught N1 N2 pi R2 square by L. I hope this is clear. Let's try to verify the thing that even if you find due to the inner coil into outer coil, you will get the same. Let's check that. So for that, suppose instead of taking current in the outer loop, I am going to take current in the smaller loop. Okay, and what is the value of current I am going to take? Suppose call it I2. Now if you are going to take I2, if you see the cross section view like this is R2 and this is R1, right? And because of the current in the I2, there will be some magnetic field. How much? B is equal to mu naught N2. We can see now this smaller coil has N2 turns and bigger coil has N1 turns. Radius of bigger is R1 and for a smaller one is R2. So we have already written this information in above, just above here. So mu naught N2 by L, where L is the length of this, into I. This is the magnetic field. Okay, I2. Now see, if you see this in the bigger coil is there, okay, whatever the magnetic field is coming because of a smaller coil, that is coming for only this small part here, okay. It is not coming for this whole part. Okay, this is not coming for the whole part. Magnetic field is only in this part. Okay, uh, because what will happen outside the very long solenoid, we know the magnetic field is zero. We know that thing. Okay, so we have to undergo that assumption, then only we'll be able to find. So what will happen? N1 phi 1 due to coil 2 is equal to Mi2 according to our definition, where we can write N1 phi 1 is how much? B, which is mu naught N2 by L into I2, and area. In the bigger coil also the flux will come only up to this part only. Why? Because outside the smaller, you can say, in this inner solenoid magnetic field is only inside, not outside that. So here pi R2 square is only going to come. That is equal to Mi2. Okay, so I2 will get cancelled out, and you can see easily that mu naught N1 N2 pi R2 square by L. The same result is going to come here, and here the value of M is going to become same. And you can see this is only our reciprocity theorem, which I have told that M, whether you find due to current in 1 in 2 or the reverse, you are going to get the same. Okay, I hope this is clear. Now, see relation between L and N. So suppose there are two coils. Okay, this one and this one. This coil is having L1 self inductance, and this coil is having L2 self inductance. Now what will happen? Because of this coils, there will be some interlinking fluxes between them. Like this coil are going to produce a magnetic field, which are going to somewhat of the flux are going to link with the another coil. Okay, so here because of this linking, some mutual inductance is going to come, and we write mutual inductance is equal to K times root L1 L2. This is a formula where K is called coupling constant. Okay, for example, if 100% means if all the whatever flux in one is there, that is going into, then K will become 1. Okay, like for some example, suppose we take a core and we take a coil here and coil here, and such that no leakage is there, no leakage in the sense all the magnetic field whatever is in there in coil 1, that is passing through coil 2, nothing is going here. In that case K will give 1. Here 100% is linkage. Okay, and in that case what you can say, mutual inductance of this coil will become simply L1 L2, where L1 and L2 are the self inductance of both the coils respectively. Okay, so I hope this is clear. So whenever we take a note point, whenever we take two simple inductors L1 L2, what happens generally we ignore the mutual inductance part, but maybe they might have some, like they are, since they are nearby, they might have some linkage like this. Like magnetic field we might link with each other. In that case, see, if link is going to support each other, means like linkage will be in such a way that the like current is in the same direction, you can say, or they are going to support. In that case, L equivalent is going to come L1 plus N2 plus twice M, where M is the mutual inductance, which is K times root under L1 L2 as said above. While if current are in opposite direction, actually these things are not too simple as shown. You'll do these things in detail in BTech. So right now I am not going in detail. So, okay, this all this how this comes you will see in BTech. Right now I'm not going this. Whatever generally is written in book, I am simply showing that. So here you can say current are in opposite direction. So current entering here and here. In the above one current are entering in the same side. So here L equivalent, here L2 will come L1 plus L2 minus twice. So this is the formula. So energy also half Li square, then instead of L we can keep L equivalent. I hope these formulas are clear. Now one is your LR circuit. The next one is your LR circuit. So first of all, first one is your, so write down first of all LR circuit. So first one is your case one is growth of current. So if you are going to use an inductor, okay, you took a battery, a resistor is also there, and you took a switch. Okay. As soon as you close the switch, what will going to happen? Some current will start flowing. Okay, and you know inductor will not let the current instantaneously become the full value. So it is going to opposite. That is the only the property of an inductor. So if you write the KVL, what is it like? E minus IR minus LdI by dt is equal to 0. Okay, so you are going to write this. Then what to write? E minus IR is equal to LdI by dt. So di by E minus IR is equal to dt by L. And now if you integrate this, where to where? Current C initially as soon as you switch on the circuit, okay, inductor will not at all allow any current. It is going to fully opposite. So initially current will 0 and finally at t time it will be some t. So 0 to t. So if you integrate it will come ln E minus IR and here minus 1 by R will come. Where to where 0 to I is equal to t by L. So this will become ln E minus IR by E is equal to minus t by TR by L. So if you write it, become 1 minus IR by E is equal to E power minus TR by L. So if you arrange it, you will get I equal to E by R 1 minus E power minus T by TR by L. And this only we write I max 1 minus E power minus T by tau. So the same tau is similar to capacitor here. Tau is time constant. Time constant. I max is maximum current, which is V by R or E by R. Okay. So tau is your L by R. Okay. Now at t equal to 0, what is the current? If you keep t equal to 0, can you see current will become 0? And we know that also. And at t equal to infinite, if you put t equal to t infinite, what will happen? Current will become simply E by R. Okay. So what you can conclude from these two things? Do you remember in a capacitor I said at t equal to 0, an uncharged capacitor is going to behave like a short circuit. But at t equal to infinite is going to behave like an open circuit. Just the reverse will happen here. At t equal to 0, an uncharged or yeah you can say an you can say uncharged. It's basically not that charged. It's energy without any energy. Inductor without any energy. Uncharged energy inductor behaves like open circuit. It's not going to allow any current. While at t equal to infinite, it behaves like short circuit. Okay. So again, like if you plot the at one more thing at t equal to tau. Do you remember I have said whatever has to happen will happen 63% is in one time constant. So in one time constant what will happen? Current will increase by 63%. So at t equal to tau, wait, I will write again. Current will become 0.63 of I max. So now the plot of graph of the graph here t and I. So this will come something like this. 0.63 of I max, here I max and T here tau. Okay, so this is the simply the charging of a inductor. Okay, now see, let's see one question before moving further. Suppose there is a capacitor and a resistor 10 ohm, 2 microfarad capacitor, and there is a resistor 20 ohm and an inductor of 5 Henry, and there is a battery of 20 volt. Find, this is I, this is I1, this is I2. Find I1 and I2 at t equal to 0 and t equal to infinity. So you have to do this question. So we know at t equal to 0, what is going to happen? The capacitor behaves like a short circuit, while inductor will behave like a open circuit. The circuit will behave like this. So here what is going to happen? I2 will become 0 and I and I1 are going to be same, and that is equal to voltage 20 by 10 2 ampere. Understood? Similarly, at t equal to infinite, what is going to happen? The capacitor behaves like a open circuit. Okay. You can also find the voltage across capacitor and hence charge across capacitor. That also you can find. And this inductor behaves like a short circuit, like this. 21. So in this case, I2, I1. So I1 is going to be 0 and I equal to I2 is equal to 20 by 20. That is 1 ampere. I hope you understood this concept. I will make you do some more questions in next class. But for now, I hope you understood this. Okay. Now, decay of RC. So LRC. So suppose there is an inductor, this is a resistor, and this is a battery. This is fully charged and current was I naught, where I naught is V by R. You know, after a long time, this inductor will be behaving like a short circuit. Now at t equal to 0, switch is closed. So what is going to happen? So even though switch is closed, okay, what will happen? The current will not suddenly going to change because that this battery will become short circuit now. So current is not instantaneously going to change. That is the property of inductor. It is going to uh, oppose the current change and it will provide energy by its own, like whatever it has stored. Now if you write the circuit equation, we will write minus IR. Suppose I is the current at any time. Okay, minus L di by dt is equal to 0. So we'll get L di by dt is equal to minus IR. Okay. Now di by I will write here only. Di by I is equal to minus R dt by L. Integrate it. The same thing. Current is I naught to I, 0 to t. And if you are going to write all this, we'll get I equal to I naught e power minus t by tau, where tau is L by R, time constant. And the plot, if you draw I versus R graph, this will come something like this, where in one time constant 63% will decay and only 0.37% is going to left. I hope this is clear to you all. Okay, so just give me a minute. Now see, there are some more cases like where one more than one resistors and all will be there, Thevenin one, which I have told in capacitor, as well as LC oscillation, which these two things I am going to discuss in next class. So hopefully whatever I told you understood. Remaining, please go through the questions and all. Whatever doubts you question look, I will try to solve and get back to you. So, okay then.